Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 3.5 and we're going to be discussing the development of a two-dimensional tiled convolution kernel. In the previous lecture we have already discussed how to write a one-dimensional tiled convolution kernel, and in this lecture we're going to extend the concept into real image files that usually are the application of a two-dimensional convolution, and then we will discuss some of the things that are more specific to the image processing aspect of two-dimensional convolution. So the objective of this lecture is for you to learn how to write a two-dimensional convolution kernel for image processing, and so we're going to look at two-dimensional image data types and API functions, and we'll learn how to use constant caching to improve performance for the mask. And then we're going to discuss how to extend the concepts of input tiles versus output tiles, thread to data index mapping, and handling boundary conditions from one dimension to two dimensions. So this slide shows the concept of a typical image matrix representation in application packages. So a lot of times we will find it desirable to pad each row of a two-dimensional matrix to multiples of DRAM burst. So in a lot of the real applications, the developers oftentimes find it desirable or advantageous to add padded elements to each row, so that the size of each row becomes multiples of DRAM burst. And by starting the first row at the burst boundary with the padding, every subsequent row will also start at DRAM burst boundaries. So this essentially allows the program to be able to better control the DRAM burst utilization in their data accesses. And if we look at the padded matrix, because we're adding elements to each row, we effectively are adding entire columns into these matrices. So here is a simple example. If we assume that we have a matrix of 3 by 3, and if the DRAM burst is 4 elements, then we need to add one more element or pad one more element into each row to make it into a full DRAM burst size. So in this case, the pitch will be 4, and one more than that the width. So in this example, the height is 3, the width is 3, and then the pitch is 4. In most of the images today are color images. That means that each pixel is not a single value, but it's actually a combination of color channels. And the most typical representation of a color image is R, G, and B, red, green, and blue. So each pixel will typically have 3 values rather than 1. And so in this example, we do not have multiple values in each element. So in this example, we say there's only one channel. However, in the lab, you will need to be able to process a color image with 3 channels in each pixel. So the padding is typically done automatically by matrix allocation or matrix importing functions. And the implementation of these functions will typically look at the hardware DRAM burst configuration and optionally add these padded elements. So that when you call the same library function, depending on the hardware that you're running the application, you might get different padding or different pitch value when you get the array matrix from these functions. So this is the picture that I would like you to remember about pitch. when you process images. So in the bottom, we show that here there is a padded matrix, conceptually padded matrix with one padded column. And then when we lay out the matrix into row major layout in the memory, you will see that there is one extra element at the end of every row in the layout. And so these elements are non-existing elements. So the important part is when we start to use linearized elements, access indices, we need to use the pitch rather than the original width when we skip over entire rows. So let's say if we want to access element M21, and originally we would multiply 2 by the width, which is 3 plus the column. However, because of the padding, we actually need to multiply the row index by pitch value so that we skip over enough of these elements, and then we can so that we can get to the right M element. So in order to access M21, we need to multiply 2 by pitch value, which is 4, and then we add 1, the column index. So this gives us 9. So this will lead us into the effective M9, which is actually, which will include the effect of the padded elements, the M3 and M7 that are non-existing in the existent in the original matrix. So now that you understand the concept of pitch and channels, we show a summary of the image matrix type that you will be using in the heterogeneous parallel programming class. So this is the data type that we will assume for images, and this is only going to be used in the host code of the machine problem. And by the time you invoke your kernel, you should have extracted the data and the width and height and the pitch and send them into the kernel for the kernel to process the data. So when you look at the host code, it should be now clear to you what the host code is doing. It's actually reading a real-life color image from a file, and then it would populate the value into all these fields in the image data. And then the host code will extract these values before it launches the kernel or do the copying of the data from the host memory into the device memory. So here are some of the API functions that you will see in the host code. So basically, we can allocate a new image. So this will be done for the output image, and we could import a image. In the process, we'll also allocate memory for that input image. So this is done by the WB import function. And we also have several utility functions that help us to extract the relevant information from the object. So the width of the image, the height of the image, the number of channels in each pixel of the image, and then we can get the pitch of the image. So all these values can be extracted by these functions, and so that we can set up the configurations properly when we launch kernels. So for simplicity, the pitch of all the matrices in this lab, in our lab, will be set to width times channels. So which means that there's just no padded elements. So after we talk about all these concepts, we'll end up using the width value for the pitch value in all the cases. So this allows you to have a simpler way of writing your kernel. However, I did want to make sure that you understand the concept so that you can easily and quickly adapt the kernel function you write for this course to handle real-life image cases where there might be a pitch, a value that is different from the width. So the use of all these API functions has been done in the host code given to you. So you don't need to understand the intricate details of all these function definitions. However, I do want to make sure that I mention these functions to you so that when you read the host code, you will be able to more confidently understand what's going on in the host code. So now we're ready to extend the concepts that we learned in the 1D kernel case into a 2D convolution kernel. So we still have the concept of output tile width. And in this case, we assume that the 2D case, we assume a square two-dimensional tile. And the output tile is still going to be smaller than the input tile. And the thread blocks are going to be configured to cover all the input tile elements. So by assuming a square tile, we're going to define a block width which is mask width -1 bigger than the output tile size, so that essentially we get the extra elements in the input tile that are needed to generate an entire output tile. So in this case, we're extending both in the horizontal direction and the vertical direction to be able to gather all the input elements needed to generate a square output tile. And so when we set up the thread blocks, we're going to be using the input tile size, which is the block width here. It's mask width -1 bigger than the output tile width. And here we assume that the mask size is 5. And in general, we should just add mask width -1 to whatever output tile width we have to get the block size. And then we're going to take the width of the image and the height of the image and divide it by the output width, tile width, and take the ceiling function to make sure that we have enough thread blocks to generate all the output elements. So here we assume that the input image and output image are of the same width and height, which is usually the case for convolution computation. So now we have an opportunity to introduce constant memory and constant caching in CUDA. So if we look at the access pattern for mask, for the convolution mask, the mask is used by all the threads, and but it's not modified in the convolution kernel. And all the threads in a warp will access the same locations of the mask at each point in time. So if we look at all the 32 threads in a warp, all those threads will be accessing element 0 at the same time, and then they will access mask array element 1 at the same time, and so on. So this is very similar to a situation where if we have a program constant or coefficient in our statements, then all the threads executing that statement is going to access the same value. So this is the origin of the name constant memory. We're storing all those values in a memory that will be aggressively cached, and then the access value from the cache will be broadcast to all the threads in a warp to even more drastically magnify the memory bandwidth by that cache. So in the newer CUDA generation, if we use const and __ restrict _ qualifiers in front of a parameter pointer, then the compiler will be able to know that this particular data structure is eligible for constant caching. So here is a simple example. You can potentially write a kernel function, and then the kernel function will receive the data portion of the input and the height of the image, the width of the image, the number of channels in the image, and then you will also need to receive the mask. So the mask is actually parameter needs to be preceded by const and __ restrict _ qualifier, so that the compiler knows that the mask elements are eligible for constant caching. So here we extend the concept of input tiles and output tiles, into 2 dimension. So here we show that when we assign the input elements and output elements to each thread, we're going to shift the output index by 2 to the left, and also the output column index by 2 to the above, so that essentially we move the thread 0 will be responsible for the corner input tile element, and it will also be responsible for the corner output tile element. So this is just a straightforward extension of the one-dimensional case. So this allows all the threads from 0 to output thread block to generate all the output elements, and then we have more of the elements to participate in loading the input elements. So this leads us into the loading of the input element. And this is also a very straightforward extension of the two-dimensional case, where we not only need to test the horizontal, which is the COL_I case, but also we need to make sure that the row indices are also within the valid range. So whenever a load of the input value is within the valid range, then we load it into a two-dimensional shared memory array indexed by the thread index y and x dimension of the thread index. And whenever it's outside the valid range, then we know that it's loading a ghost element. So in this particular case, we still assume that we have the policy of setting ghost element to zeros. So here, if we look at this code, we have a linearized input axis. And if the pitch is different from width, we should use the pitch value in this multiplication. However, because the pitch and width are the same for our labs, you can just use width. So whenever you need to extend this kernel to a more general image processing kernel, then you need to use the pitch value, and you need to supply that pitch value into the kernel for appropriate access. And once we finish loading, remember you will need to use a barrier synchronization in between these two, the loading and the computation. So when we enter the computation, just like the one-dimensional case, only the threads within the output tile range should participate in the computation. And so we're going to not only test the X thread index, but also the Y thread index. Otherwise, it's a straightforward extension of adding another loop so that we would do a two-dimensional access to the shared memory and the mask and accumulate into the output. At the end of the kernel, we're going to write output, and we're going to need to test whether the row index and the column index of the output index are within the valid range. So this makes sure that we don't end up writing into non-existing or ghost elements. So this gives us the expression for writing the output. So so far we have discussed the code in terms of a single channel pixel format. And you need to look at the machine problem description on the GPU, web GPU, to see some a instruction about how to adapt this kind of code to accommodate a multi-channel pixel. And you also need to know that the width need to be adapted to a pitch value if we're handling a more general image file. So this concludes the discussion of a two-dimensional convolution kernel. At this point, you're ready to do the machine problem for two-dimensional convolution. And for those of you who would like to learn more about constant memory usage or convolution in general, I'd like to encourage you to read section 8.3 of the textbook. Thank you.